The second derivative test. As we discovered, the first derivative is a useful tool in finding local extrema for functions. In addition, the second derivative was helpful in finding intervals of concavity of functions. As it turns out, the second derivative can also give us information about local extrema of the original function. Next, we will explore how to do this using the second derivative test. It's worth noting that the second derivative test does not replace the first derivative test. Both are useful tools. In fact, at times, the second derivative test isn't even necessary. The second derivative test states, given that x equals c is a critical value of f prime of x equals 0, and that f prime of x is continuous at x equals c, then if f double prime of c is less than 0, then c is a local maximum. And if f double prime of c is greater than 0, then x equals c is a local minimum. And there was quite a bit of information on that second derivative test definition. Let's try breaking it down to make it easier to understand. So the critical values from the first derivative tell us where there are potential local maxima and minima. The second derivative test tells us that if the second derivative is positive, the function is concave up, and therefore there is a minimum. So if f double prime of c is greater than 0, it means it's concave up, and therefore that extrema value that we found is therefore a minimum. Similarly, if the second derivative is negative, the function is concave down, and therefore there's a maximum. So if f double prime of c is less than 0, then you have this shape and you have a maximum. X equals c is a critical number from where the first derivative is equal to 0 and the first derivative is continuous there. The second derivative test provides an alternative method for classifying the extrema. However, there are situations where the second derivative test would fail to supply any information about the extrema. This is when f prime of x does not exist, f prime of x equals 0, but f double prime does not exist, and when f prime of x equals 0 and f double prime of x equals 0. In any of these scenarios, the first derivative test would need to be used. Using the second derivative test, determine if the function below has any relative extrema. The first step is to find the first derivative and determine its critical values. And we're going to use the power rule. 2/3 times 3 is 2, x to the second. And then 5/2 times 2 is 5, so plus 5x, and then minus 12. And then if we set this equal to 0 and solve, we can determine that the x values of 3/2 and -4 are critical values. Next, find the second derivative. So if f prime of x is 2x squared plus 5x minus 12, our second derivative, or f double prime of x, is going to be 4x plus 5. Once we have the second derivative, we can substitute these critical values into it in order to determine if it's positive, concave up, or negative, concave down. So if we substitute 3/2 in there, 4 times 3/2 is 6, plus 5 is 11, and then f double prime of -4 is going to be -16 plus 5, which is -11. A positive value means that the graph is concave up, so this positive 11 means that at 3/2 we have a local minimum, and a negative value for concavity means that the graph is concave down, and this x equals 4 value is a local maximum.